Hi folks, my name is Joe Bland, and I am representing the Sacramento L5 Society, one of the National Space Society's oldest chapters. Today, I'm going to present a summation of an analysis our chapter began in March of 2014 called Powering a Moon Base Through the Lunar Night. For further details, the full analysis may be found on our website at www.sacl5.org/moonbase.html under the heading Solar Energy Will Power the Moon Base. Here are the topics I'll be briefly covering today. In March of 2014, employees of NASA Ames in California began an informal brown bag lunch working group, the stated and clearly ambitious goal of which was to develop a plan for establishing and operating a NASA moon base that could be constructed within 10% of the total NASA budget. That working group was attended by Sacramento L5 member Michael Abramson, who brought it to our attention at our next chapter meeting. About 3 months earlier, two sophomore college students whom I was helping to mentor, Akhil Kumar and Krishna Bhavana, studying at Rajiv Gandhi University in Nuzvid, India, entered the 2014 National Space Society-sponsored Sunset Design Competition. Akhil and Krishna proposed beaming space-based solar energy to Earth by way of a laser beam located in geosynchronous orbit. In May, their presentation won the competition's $10,000 first prize. A month or so earlier, I had mentioned to Akhil and Krishna that it seemed to me their laser approach could be useful in another way. That is, by placing such a laser at the Earth-Moon system's Lagrange point 1, or EML1. The laser could be used to broadcast power to the lunar surface during the lunar night. After hearing from Michael about the NASA Ames working group, it occurred to me that one solution to powering their proposed moon base would be to use that EML1 laser concept. Thus began our chapter's attempt to answer this question. What is the most practical way to sustain a permanent moon base through the half-month-long lunar night? The 2009 NASA Concept Study. By January of 2015, our analysis was essentially complete when a set of slides was discovered on the internet entitled NASA JSC Lunar Surface Concept Study. Since the much more thorough NASA study and our analysis covered much of the same ground, we immediately undertook an extensive rewrite. The two reports had much in common. As in our analysis, NASA looked at solar as the primary source of energy. We, and I presume NASA, looked briefly at radioisotope thermoelectric generators as well, but concluded they were simply too massive for our purposes. Finally, like our analysis, the NASA analysis examined surface energy storage by flywheel, electric, chemical, and thermal systems. The preferred system recommended in the 2009 NASA study was a PV solar array-powered cryogenic storage regenerating fuel cell system, or CRFC. NASA calculated that a 5 kilowatt continuous delivery CRFC system would store 2,000 kilowatt hours with a system energy density of 1.15 kilowatt hours per kilogram. The study's alternate preferred system was a fixed orbit laser system, or FOLS, with a 16.1 hour orbit period that required a surface receiver installation with 525 kilowatt hours of energy storage. Electric propulsion. As recognized in the NASA study, an electric propulsion system can be used for orbital station keeping, which can be broadly defined as maintaining an object in space in a preferred position or orbit. Some numbers were available in the NASA concept study for such systems. A second relevant use for an electric propulsion system wasn't specifically covered in the NASA study. Mass doesn't necessarily have to be lifted directly from Earth to its final destination. Once in low Earth orbit, or LEO, an electric propulsion system can be used to orbit out from LEO. For some of our calculations, we assumed that the propellant and electric propulsion drive used to move a mass from LEO to either lunar orbit or EML1 will equal 30% of the transported mass. Lunar Polar Surface Mounted Multi-Array System. One approach that was not explored in the 2009 NASA study concerns high mountain peaks at the moon's poles. It is well known that Shackleton Crater, which is located almost exactly at the moon's south pole, has large peaks which come close to being so-called peaks of eternal light, defined as mountain peaks that always see sunlight. And it has been noted that combined, 2 points only about 8 kilometers apart on the rim of Shackleton Crater are illuminated a combined 94% of a lunar year. Use of such peaks to aid in powering a moon base was suggested by chapter member Michael Abramson in February of 2015. Michael proposed the establishment also of a moon base near those 2 peaks on Shackleton's rim, and the construction of solar energy collectors on those peaks. The energy thus collected would then be directed to the nearby moon base. Options to connect these points to the moon base include electric cables, optical waveguides, lasers, microwaves, and solar energy reflectors. In our analysis, we presumed that the maximum storage requirement for such a system would be about 36 hours, not including backup storage. Michael then went on to propose the establishment of a lunar energy grid. Over time, this grid could be grown, expanding into the areas which only see sunlight for half of the month-long lunar day. Assuming the grid were built out in opposite directions from the pole simultaneously, the grid as a whole would be able to continuously see approximately half the solar collectors producing energy at any given time. Yet another aspect of a prospective moon base that was not specifically mentioned in the NASA concept study is the absolute requirement for an emergency backup system, or EBS. In our analysis, a prudent backup quantity is assumed to be 120 kilowatt hours for a 15 kilowatt continuous nighttime moon base energy system. Our analysis concluded that lithium-sulfur batteries presently appear to have the best specific energy, or kilowatt hours per kilogram. However, other systems would benefit greatly from in situ resource generation, or ISRU, and would become competitive fairly rapidly once manufacturing on the lunar surface began. A specific energy of 0.5 kilowatt hours per kilogram for lithium-sulfur batteries has been used in our analysis as the basis for energy storage mass calculations for all systems. Orbiting laser systems. NASA studied the possibility of an orbiting solar-powered laser system. However, it restricted its study to an orbiting laser system that was only powered and fired when it was in direct sunlight and when it was in direct line of sight with the moon base. Laser systems at EML1 and EML2. For any 2 bodies in space rotating about a common center, or barycenter, there are 5 points of special interest called Lagrange points. For the Earth-Moon system, they're called EML1, EML2, EML3, and so forth. In the case of EML1, this point is between the Earth and the Moon and along a line between their centers of gravity. In the case of EML2, this point is along the same line, but beyond the back of the moon. The Lagrange point marks positions where the combined gravitational pull of the two bodies precisely matches the centripetal force required for the points to orbit with those bodies. In their study, NASA looked at and rejected as impractical an approach to continuously powering a moon base that involved parking a solar-powered laser system at EML1 or EML2. Solar-pumped laser systems. NASA presumed the use of photovoltaic or PV cells for their study, including as a means for powering their laser systems. Our chapter also studied the use of photovoltaic-powered laser systems, or PVLS, but also considered a different technique for powering a laser, that is, direct solar pumping. In a solar-pumped laser system, or SPLS, the solar insolation is concentrated directly on the laser, bypassing the electrical conversion system. Efficiencies for the SPLS and the PVLS are expected to eventually be about the same, but the SPLS appears to have a higher specific power even at present efficiencies. Orbiting energy storage systems. NASA did not consider the use of an orbiting laser system in conjunction with an orbiting energy storage system. Note that a satellite that is not in sun-synchronous lunar orbit will move continually into and out of the moon's shadow. Adding an orbiting energy storage system permits an orbiting laser system to continue beaming energy even when the satellite is in shadow. An orbiting energy storage system can also be used with a sun-synchronous orbiting system to store energy until the laser system can regain direct contact with the lunar base. By leaving parts of the energy storage system in orbit rather than moving them to the lunar surface, overall project mass can be reduced, since rocket motors, fuel, and so forth can be scaled back. NASA also never considered the possible use of a deflecting system. A deflecting system, as the term implies, permits a laser beam to be deflected. In certain circumstances, a deflecting system in lunar orbit may permit nearly uninterrupted laser beaming from an orbiting solar-powered laser system to a given location, thus obviating the need for energy storage either in orbit or on the lunar surface. A deflecting system can also find use in other ways. It is possible to envisage a series of non-orbiting deflection modules placed directly on the lunar surface to transfer beamed energy to other locations. Indeed, a surface-based solar-powered laser system at the lunar poles may beam solar-powered laser energy to an orbiting deflecting system, distributing via laser lunar pole-generated solar energy to other locations on the moon. A deflecting system can also find use in other ways. It is possible to envisage a series of non-orbiting deflection modules placed directly on the lunar surface to transfer beamed energy to other locations. Indeed, a surface-based solar-powered laser system at the lunar poles may beam solar-powered laser energy to an orbiting deflecting system, distributing via laser lunar pole-generated solar energy to other locations on the moon. Solar sail propulsion and the gravity winch. One of NASA's reasons for rejecting the use of a laser at EML1 and EML2 was the determination that station keeping, even by electric propulsion, will be prohibitively expensive in fuel cost. That turns out to not be true. A solar sail propulsion system can be used to enhance or even replace an electric propulsion system for station keeping purposes at EML1 and EML2. A solar sail propulsion system is advantaged over an electric propulsion system because of its ability to modify a spacecraft's position without using fuel. A fascinating and related idea is the use of reels to pull in or let out either solar sails or even simple gravity anchors relative to a space-based platform. Using gravity anchors in this manner constitutes the concept of a gravity winch. A gravity winch is basically a pair of reeled tethers that are dropped down gravity wells from a neutral gravity point, such as a Lagrange point. In the case of a platform orbiting at EML1, a tether can be dropped from the orbiting platform down the gravity wells of both the Moon and the Earth. Shifting the gravity anchors from one side of the platform to the other allows the EML1 platform to balance between the two gravity wells, similar to the way a pole helps a tightrope walker balance. Note that this may be done with simple electric motors and without expending any mass. Intriguingly, an old document has recently come to light on the internet. This document, written in 1963 by Giuseppe Bepi Colombo, who is best known for his work on the Mariner 10 mission to the planet Mercury, and whose name has been given to the Bepi-Colombo Joint ESA-JAXA mission to Mercury coming up in a few years, strongly supports both the concept of solar sail station keeping at EML1 and the concept of the gravity winch. The oscillating Lagrange point orbit. Presently, station keeping in the vicinity of Lagrange point 1, 2, or 3 is accomplished by a relatively stable three-dimensional halo orbit. However, chapter member Roger Arnold has proposed what appears to be a unique alternative that we call the oscillating Lagrange point orbit, or OLO. The OLO seems to be largely a two-dimensional orbit in the two-body orbital plane. Over the month of a lunar rotation, the theorized course of an OLO can be expected to be found approximately along the 6,400 kilometer line of travel of EML1. That line of travel is coincident with the Earth-Moon center line and is described by the Moon's elliptical movement between perigee and apogee as it orbits around the Earth-Moon barycenter. As Mr. Arnold put it, the metastable neutral point that the station should track is not the L1 point, wherever it happens to be at any given moment. Rather, it is a point in the 6D phase space for the system, i.e., both position and velocity vectors must be right. When they are, the station describes an oscillating orbit that passes through the L1 point twice per month. Once the station achieves the neutral point, I believe the only station keeping that's needed is to correct for drift due to measurement errors and unaccounted solar radiation pressure. The neutral point that the station follows will oscillate with the L1 point, but with lesser amplitude and lagging in phase. The proper analogy is balancing a weight atop a pole whose base is oscillating back and forth. The OLO appears to be able to operate in much closer proximity to the Lagrangian point with which it is associated than a halo orbit. This is useful for reducing size and complexity of the laser tracking system for beaming energy to the lunar surface from EML1 or EML2. Aggressive laser collimating. Finally, perhaps the most powerful aspect of laser use in space that was not found in the NASA concept study was the possibility of using aggressive laser collimating. This exciting possibility was also originally suggested by chapter member Roger Arnold. Collimating a laser beam essentially expands the laser beam at the source using either a series of lenses or reflecting mirrors. Lenses are preferred over mirrors as they lose much less light energy in the process. Counterintuitively, expanding a laser beam before it is broadcast over a distance actually decreases the angle of divergence. And aggressively collimating a laser beam, that is, dramatically increasing the diameter of the beam, allows the beam to be transmitted over a great distance with very little divergence. Mr. Arnold noted that aggressive collimation becomes practical in the weightless vacuum environment of space, where a thin film Fresnel collimating lens might only be a few mils thick. How would this impact space laser designs? As an example, in the NASA 2009 study, a laser system at EML-1 would create a lunar surface spot diameter of 119 meters, or a circular area of 44,488 square meters. Assuming we increase the diameter of the aperture from 1 meter to about 9.6 meters in diameter, we would reduce the lunar surface spot diameter to 12.6 meters, or a circular area of about 125 meters squared. In situ resource utilization. Our analysis concluded that several energy storage systems, for example, thermal energy storage, would benefit greatly from in situ resource utilization, or ISRU, and would become competitive fairly rapidly once manufacturing on the lunar surface began. Clearly, systems that rely more on energy storage will be more positively affected by any future improvement in energy storage technology or the development of ISRU on the moon. However, all systems will be positively affected to some degree, since all systems will need some minimum amount of backup power in case of emergency. Comparative calculations methodology. We need to spend a little time speaking of the methodology we use for comparing systems within our analysis. In our analysis, we spend a lot of time analyzing mass. Our percentage calculations methodology involves two elements. First, we attempt to estimate the mass for each system at various points in space. Second, because it obviously takes less force to put a given mass into LEO than into lunar orbit, and less force to put a mass into lunar orbit than on the lunar surface, it is useful to use a given lift capacity to determine relative masses of different systems in different locations. In our analysis, the lift capacity is defined in SpaceX Falcon Heavy, or FH, units. It was determined that one FH unit's lift capacity can put about 53,000 kilograms into LEO, about 17,216 kilograms into either EML-1 orbit or lunar orbit, and about 5,739 kilograms on the lunar surface. Looking now at other systems we analyzed, NASA estimated that for a 5 kilowatt system, it would require about 2,000 kilowatt hours of energy storage capacity to make it through a lunar night. Our number was in general agreement, although our study assumed a 15 kilowatt system, requiring about 6,000 kilowatt hours of energy storage capacity. Clearly, therefore, we can compare the masses of the various systems. Thus, the comparative cost of each system comes down to comparative masses. As an example of what that implies in energy storage capability, using a Model S Tesla battery pack weighing 600 kilograms each, we'd get about 60 kilowatt hours of storage, giving us a specific energy of 0.1 kilowatt hours per kilogram. Thus, in order to continuously produce 5 kilowatts for half a month during the lunar night, we'd need the equivalent of 33 Tesla Model S batteries on the lunar surface, equal to a total mass of 20,000 kilograms. In our lift capacity units, that would equal about 3.5 FH, that's Falcon Heavy, units. Implications. So what do all these missing elements in the NASA concept study mean? Recall that NASA looked at and rejected, as impractical, the concept of parking a solar-powered laser system at EML1 or EML2. However, in making its determination, NASA did not consider the possibility of aggressive laser collimating. With aggressive laser collimating, Lagrange points suddenly become eminently practical locations for solar-powered laser satellites. EML1 and EML2 represent point locations in the moon sky that effectively don't move since they're along the Earth-Moon common axis. Energy from the laser beam is a continuous process, except total eclipses of around 5 hours maximum, perhaps twice a year. With no atmosphere, there is no extraneous absorption or diffraction of laser energy. With no ecology in harm's way, the laser beam can be increased in intensity. The laser system can be grown in a modular manner. Thus, if we orbit a second laser system that is equal in all respects to the initial laser system, we will double the input to the main surface receiver on the moon with no change to the surface receiver whatsoever. Power plant modularity inherently builds in a redundancy that is very important to ensuring a moon base's long-term survival. Use of a simple beam redirecting apparatus would permit a laser beam to be directed at the floor of the Shackleton crater on the moon's south pole. Laser collimating also makes the concept of orbiting laser systems much more practical by greatly reducing the size of the laser receiver. Reduced size means reduced mass. This mass reduction is magnified even more by use of an orbiting energy storage system, and magnified even further through the use of a deflecting satellite system. Tracking more closely to EML1 than a halo orbit would make it far easier to permit the dropping of a tether towards the moon. That in turn would greatly enable the eventual creation of a practical lunar elevator, hugely reducing the cost of colonizing the moon and accessing lunar resources. A stabilized platform in the vicinity of EML1 that won't require continual shipments of station-keeping fuel to stay in orbit means it's easy to park material depots there. Finally, because EML1 is inherently unstable, rather like a frictionless hill that's continually in motion, it is by its nature completely free of space junk. I'm sure there are other advantages, but these alone should be sufficient to identify the oscillating Lagrange point orbit, or OLO, as an extremely valuable piece of space real estate. Findings. On our website at www.sacl5.org/moonbase.html, under the heading Solar Energy Will Power the Moon Base, you will find a link entitled Appendix 1 of the Full Analysis. The link is to a table entitled Moon Energy Systems, 15 kilowatt lith capacity in Falcon Heavy units and dollar equivalents. In that table, all systems are calculated for a 15 kilowatt continuous lunar night output. The systems are shown sorted from low cost to high cost by the column Total FH dollars without EP. FH units, or Falcon Heavy unit dollars, are calculated based on $1,200 per kilogram, in accordance with a statement by SpaceX Chairman Elon Musk that, ultimately, I believe $500 per pound or less is very achievable. Note that F8 unit dollars do not include any costs associated with developing the various systems shown in the table. Conclusions. The findings of the Sacramento L5 Society analysis are very much first-order approximations. In addition, the analysis is still a work in progress. However, in light of the dramatic nature of those findings It is felt that the systems in question merit a far more in-depth analysis than the Sacramento L5 Society is capable of delivering. It is hoped that this effort of ours will inspire the undertaking of such an in-depth analysis by NASA or some other interested party, to the benefit of all who dream of mankind moving outward into the universe.